It's a funny thing about just looking out a window
Oh, how so?
where you stare out at a mountain range or maybe a dense forest or, honestly, even just a puddle on the street reflecting a gray sky. And your brain just accepts it, like it's real.
Right, yeah, the physics just happen naturally.
Exactly. The light bounces off the water, the wind kind of ripples the surface, the dirt on the bank slowly erodes over decades. But then you turn your head, you look at your computer monitor, and you see the exact same mountain. You see the exact same puddle.
And your brain, assuming the software is good enough, just accepts that too.
It does. It completely buys it. And the wild part to me is what it actually takes to pull off that trick. Because out the window, the universe is just doing the math for free.
Yeah, but on your screen, your GPU is sweating.
It's sweating bullets. It is millions of complex equations every fraction of a second, solving geometry, physics, optics, just so you don't realize you're actually staring at a flat, two-dimensional grid of glowing squares.
When you really break it down to its most fundamental components, it is a mathematical magic trick. Literally, every leaf, every shadow, every rock you see is the result of layered algorithms.
And that is exactly what we are unpacking today. So I want to send a very special shout out to a specific group of listeners joining us on this deep dive.
Absolutely.
We are talking to the Busson Sigma Scholars of Edward Little High.
Welcome.
Yeah, we've got a custom-tailored deep dive just for you today. Because look, to maintain that Sigma grind set, you need to truly appreciate the media, the simulations, and the digital spaces you interact with every single day. And to do that, you have to understand the absolute bleeding-edge tech powering it all.
Which means getting into the raw math.
Yeah, the math and the algorithmic logic.
Because knowledge becomes truly powerful when you can look at a final product and reverse engineer exactly how it was built. So today, we are looking under the hood of digital reality.
So let's lay out the mission for this deep dive. We're going to decode the hidden layers of linear algebra and artificial intelligence that seamlessly work together to trick our eyes. We're talking infinite photorealistic environments that somehow don't instantly fry our computer hardware.
And we've got a hefty stack of sources to get through to do this.
A massive stack. We are pulling from academic papers on procedural terrain generation, diving deep into geometric level of detail rendering, which is called GLOD.
Right.
We're exploring some wild research on using transformer-based AI to generate L systems for trees, analyzing real-time fluid dynamics, and looking at Unreal Engine 5's nanite and lumen technologies.
Oh,
And breaking down the core principles of physically based rendering, or PBR.
it sounds like a lot of disparate topics, I know. But there is a clear, causal through line here. We are going to trace the journey of a digital world from its absolute infancy.
Like raw matrices and numbers.
Exactly. From raw code all the way to a fully realized, breathing 3D environment. We want to show not just what these concepts are, but exactly why each mathematical decision is absolutely critical to the final image you see.
So I want to start at the bedrock. Literally.
The ground we walk on.
Yeah. Let's talk about the actual ground in these virtual worlds.
Yeah.
If you were building a simulation, a digital twin of a city, or a massive open-world game, you simply cannot have a team of digital sculptors handcrafting every single rock, valley, and hill across a map the size of a continent.
It would take centuries of human labor. It's just not feasible.
Right, so that massive bottleneck is what birthed procedural terrain generation.
Instead of manually sculpting a mountain, saving that massive 3D file, and storing it in your computer's memory, you teach the computer how to grow a mountain on its own.
You build the world algorithmically.
Yes, you give the computer a mathematical formula, and it just generates the landscape on the fly as you walk through it.
And the holy grail of this technique, the algorithm that basically built the modern digital landscape, is Perlin noise.
Named after Ken Perlin.
Yeah, he developed it back in the early 1980s for the movie Tron, actually.
Which makes sense. He was frustrated with how perfectly flat and, plastic early computer graphics looked.
Right, he wanted a way to introduce controlled randomness, like natural-looking chaos.
It's a brilliant piece of history. But to understand how Ken Perlin's noise actually generates a mountain, our source material insists we have to take a step back and root this entirely in linear algebra.
Oh boy, math class.
It's unavoidable. You cannot understand procedural generation without understanding vectors and matrices.
Okay, I can take the lead on the basics here. For anyone who needs a quick refresher, linear algebra is essentially the math of spaces and transformations. And the most fundamental building block there is a vector.
Right.
You can think of a vector as a quantity that has two things: magnitude, which is its length, and direction.
A helpful way to visualize it is just as an arrow pointing in a specific direction in space.
Perfect. So in a 2D plane, like a flat piece of graph paper, a vector might just be defined by an x and a y coordinate. It tells you how far to go horizontally and how far to go vertically.
And in 3D space, it's x, y, and z.
Right. And vectors have some key properties. You can scale them, which is
Sure.
called scalar multiplication, which basically just means stretching or shrinking the arrow without changing the direction it points.
Yeah, but where it gets vital for terrain generation is a specific operation called the dot product.
Ah, the dot product.
It is arguably the most important mathematical operation in all of computer graphics. It takes two vectors, and instead of creating a new vector, it collapses them down into a single scalar value.
Just a regular number.
Just a normal number, exactly.
Let's break down how that calculation actually works before we talk about why it matters.
Mathematically, it is very straightforward. You take the corresponding components of the two vectors, multiply them together, and add up the results.
So if I have vector A with components by 1 and y1 and vector B with components by 2 and y2, the dot product is just by 1 times by 2 plus y1 times y2.
That's the arithmetic, yes.
Okay, but what is the geometric meaning? When a game engine calculates a dot product, what is it actually trying to find out?
It is looking for an alignment score.
An alignment score.
Yes. The dot product measures how much those two vectors point in the exact same direction. In physics and geometry, the dot product of two vectors is equal to the magnitude of the first times the magnitude of the second times the cosine of the angle between them.
The cosine of the angle. That's the secret sauce right there.
It really is. Think about how a cosine wave works. If the two vectors are pointing in the exact same direction, the angle between them is 0.
And the cosine of 0 is 1.
Exactly. So the dot product is maximized. It gives you a high positive number.
And if they are perpendicular, like if they form a perfect 90-degree corner.
Well, the cosine of 90 degrees is 0. Therefore, no matter how long those two vectors are, their dot product is exactly 0. They share absolutely no directional alignment.
Got it. And if they point in opposite directions?
The angle is 180, the cosine is -1, and you get a negative dot product.
I want everyone listening to hold on to that concept of the alignment score, because when we start shaping our procedural mountains, that dot product is going to determine whether a patch of dirt gets pushed up into a peak or pulled down into a valley.
It's the engine of the terrain.
But there's one more piece of linear algebra we need to establish from the sources. Matrices.
Right. A matrix is basically just a rectangular grid of numbers.
Now, a lot of people might remember standard matrix multiplication from school. You know, that really complex row-by-column operation where you slide across rows and down columns.
Which is used all the time in graphics for rotating cameras or moving objects.
Yeah, but the academic papers we are analyzing today highlight a completely different operation for terrain, the Hadamard product.
Yes, the Hadamard product is much simpler than standard matrix multiplication, but it is incredibly powerful for processing massive grids of terrain data.
How is it different?
Instead of that complex row-by-column dance, the Hadamard product is strictly element-wise.
Meaning you just match up the grids?
Precisely. You need two matrices of the exact same dimensions. You take the number in the top left corner of matrix A, and you multiply it by the number in the top left corner of matrix B. Then you move to the next slot and do the exact same thing.
Oh, I can totally see how that applies to world building.
Yeah.
So if I have a massive matrix that represents the raw elevation of my terrain, like a million numbers representing heights, and I have another matrix of the exact same size that acts as a mask.
Like it may be filled with zeros where the ocean should be and ones where the land should be.
Exactly. I use the Hadamard product. Any height multiplied by the mask's 0 becomes 0 completely flattened out for the ocean. Any height multiplied by 1 stays exactly the same for the land.
It lets developers apply weights, masks, and environmental filters across millions of data points simultaneously without having to write complex, slow, nested loops.
All right, so we have our mathematical tools,
Yeah.
vectors, the dot product, and matrices. Let's put them to work. Let's walk through the actual algorithm of Perlin noise step by step. We open our software, we have a blank digital void. How does the very first patch of dirt actually appear?
It begins with a grid. Imagine throwing an infinite sheet of graph paper over your digital void. The intersections of all those horizontal and vertical lines create points, which we call lattice points.
Okay.
This grid divides the world into square cells.
All right, I have my graph paper. Let's say I want to figure out the exact elevation of a single point in the middle of one of these squares. Coordinate x, y.
The first thing the algorithm does is look at the four corners of the square cell that contains your point.
The four lattice points surrounding me.
Correct. Now, at each of those four corners, the algorithm assigns a gradient vector. You can visualize this as a tiny arrow stuck into each corner.
Okay, 4 arrows.
But these arrows don't point directly at you. They point in pseudo-random directions. Often, just to save computational power, the engine will pick these directions from a predefined set, like 12 vectors pointing toward the edges of a cube.
So I have 4 corners, and each corner has a random arrow sticking out of it. What do these arrows actually represent?
They represent the slope or the directional influence of the terrain at that specific corner.
Yeah.
They dictate how the land wants to tilt.
But hold on. If these gradient vectors are randomly assigned, how does the terrain stay consistent?
What do you mean?
Like, if I build a cabin on a mountain, walk 10 virtual miles away, and come back, that mountain needs to still be there. The engine can't just generate new random arrows every time I look at it, or the terrain would literally boil and change shape every single frame.
That is the fundamental challenge of procedural generation, creating randomness that is repeatable. And this is where the permutation array comes in.
Permutation array.
It is an elegant data structure designed to solve exactly this problem. The algorithm does not generate a random number on the fly.
Uses a lookup table.
Yes. The source material details this specifically. The standard implementation uses an array of 256 integers, which is simply the numbers 0 through 255.
Like a deck of 256 unique cards.
Exactly. You take that deck and you shuffle it once, using a seed value. Once it is shuffled, it never, ever changes.
Ah, the seed. Like when you typed a seed into Minecraft.
Precisely. Now, whenever the engine needs a random gradient vector for a specific grid coordinate, say coordinate 510, it does some fast math on those numbers to pick an index and pulls a number from that shuffled array.
And because the array is static, coordinate 510 will always pull the exact same number.
Which corresponds to the exact same gradient vector every single time.
So the randomness is baked into the initial shuffle, but the retrieval is perfectly consistent.
Yes.
But the paper we read highlighted a really clever trick regarding this array. It isn't just 256 numbers. The developers duplicate the entire shuffled array and stick it onto the end of itself, making it an array of 512 numbers. Why?
That is a brilliant performance optimization trick to handle boundary conditions and wraparound.
Let me see if I can unpack that with an analogy.
Go for it.
Let's say you are calculating the noise at the very edge of your world chunk. The math is looking up the values in your deck of cards. You are at coordinate 255.
Right at the end of the array.
Right. And the algorithm looks at the next point over to figure out how to blend the terrain, so it asks for the 256th card. But your deck only goes from 0 to 255. In our normal program, asking for an index that doesn't exist causes an out-of-bounds error and just crashes the software.
Or, to avoid the crash, you have to write an if statement. You have to tell the computer, if the index is greater than 255, loop back around and subtract 256.
But if statements slow down a GPU.
Massively.
Yeah.
If you are rendering millions of pixels, millions of if statements will destroy your frame rate.
So instead of doing modular arithmetic, they just shuffle 2 identical decks of cards together. When the computer accidentally asks for the 256th card, it smoothly pulls the first card at second deck.
It inherently loops. The terrain seamlessly wraps around without any heavy mathematical calculation.
That is a beautiful example of sacrificing a tiny bit of memory, just storing 512 numbers instead of 256 to drastically increase computational speed.
It really is. So now we have our 4 corner lattice points, and using our permutation array, we have consistently assigned a gradient vector to each one.
We have the 4 arrows at the corners, but we still need the actual height of the terrain at my specific location in the middle of the cell.
Right. To find that, we calculate a second type of vector, displacement vector.
Okay, what's that?
From each of the 4 corners, we draw a new arrow pointing directly to your specific XY location.
Okay, so now at each corner, I have 2 arrows. I have the pseudo-random gradient vector that was assigned by the array, and I have the displacement vector that points from the corner straight to me.
And this is where the dot product returns.
Huh?
For each corner, you calculate the dot product between the gradient vector and the displacement vector.
The alignment score.
Exactly. You are basically asking the math, how much does this corner's natural slope align with the direction of the point I'm trying to calculate?
So if the corner's gradient vector points directly toward me, the dot product is positive and high.
Yes, that corner wants to pull the terrain upwards at your location.
And if the gradient vector points away from me, the dot product is negative and it pushes the terrain down.
Exactly. So you do that dot product calculation for all 4 corners.
Now I have 4 scalar values. Just 4 numbers representing the height influence from top left, top right, bottom left, and bottom right.
The final step is to blend them together based on where you are standing inside the cell.
Because if I'm standing very close to the top left corner, that corner's dot product should have the strongest influence on my height, right?
Correct. And as you walk toward the bottom right, the influence shifts. You interpolate between the 4 values based on distance.
Now, a lot of people might think, well, just draw a straight line between the values.
Yeah.
Like, if point A is height 0 and point B is height 10, and I'm exactly halfway between them, I should be at height 5.
Which is linear interpolation.
Right. But the sources are very clear that linear interpolation completely ruins Perlin noise. Why is that?
It comes down to how linear interpolation handles the boundaries between the grid cells. A linear interpolation produces a straight line. The problem isn't the line itself, it is what happens when one line meets another line at the edge of a cell.
They form a corner.
Yes. In calculus terms, the first derivative is not continuous. If you have a slope going steadily up and it crosses into a new grid cell where the slope is going steadily down, linear interpolation just crashes them together.
You get a sharp, unnatural peak, like a literal geometric crease in the terrain.
A jagged polygon spike sticking out of your hill, and human eyes are incredibly sensitive to those sharp edges. It totally destroys the illusion of natural terrain.
So how do we fix it?
To solve this, Ken Perlin introduced the fade function.
The fade function.
It is a mathematical curve used to ease the interpolation parameter. Instead of moving from 0 to 1 linearly, you pass your position through a specific polynomial equation.
The original was a cubic function, I think.
It was, but the modern standard, which Perlin actually updated in 2002 to fix some lingering visual artifacts, is a quintic polynomial.
And the paper lays it out. It's f of t equals 6t to the 5th minus 15 to the 4th plus 10t cubed.
Yes.
That looks like a nightmare of an equation to calculate millions of times a second. Why that specific complex polynomial?
It was chosen precisely because of its derivatives. In calculus, the first derivative of a function tells you the slope, the rate of change. The second derivative tells you how fast the slope itself is changing the acceleration of the curve.
Okay, I'm with you.
This specific quintic function has a magical property. At the start of the curve, when t equals 0, and at the end of the curve, when t equals 1, the value of the function is 0 and 1, just like linear interpolation.
Right.
But, crucially, its first derivative is exactly 0 at both ends, and its second derivative is exactly 0 at both ends.
Wait, meaning that as the curve approaches the edge of the grid cell, it completely flatlines.
Yes. It flattens out perfectly horizontally before it crosses the boundary.
Oh, wow. Because the slope is forced to 0 at the boundary, every single grid cell connects to its neighbor with a perfectly flat, seamless joint.
Exactly. There are no sudden changes in direction, no acceleration into the boundary. The abrupt transitions are mathematically eliminated. You get beautiful, rolling, continuous waves of terrain.
That is fascinating.
Yeah.
We used heavy calculus just to sand down the digital edges of our world.
It's essential.
But here's the catch, though. If you just look at a raw output of basic Perlin noise, it looks kind of like blurry, soft clouds. It doesn't look like a real mountain range.
No, it doesn't.
Real mountains have jagged peaks, they have boulders, they have tiny crevices. A perfectly smooth derivative 0 curve doesn't look like geology. How do we get that granular detail?
A single layer of Perlin noise will only ever give you those soft clouds. To build true geological complexity, developers use a technique called fractal Brownian motion, which is commonly abbreviated as FBM.
Fractal, meaning patterns that repeat at smaller and smaller scales.
Precisely. The concept is that you take your smooth Perlin noise and you layer it on top of itself multiple times. Each layer is called an octave.
Just like octaves in music. A higher octave is the same note, just vibrating at a faster frequency.
The analogy holds perfectly. The first octave is your base layer. This defines the massive, continent-sized shapes and the broad, smooth mountain ranges. Then you generate a second octave of Perlin noise and add it to the first.
But you don't just add an identical layer, right?
No, you tweak 2 fundamental mathematical parameters, lacunarity and persistence.
Let's define those for the scholars. Our academic sources spend a lot of time on how these 2 variables dictate the entire look of the world. What is lacunarity?
Lacunarity, which is usually represented in math by the Greek letter lambda, controls the frequency scaling between the octaves. In most engines, lambda is set to a default of 2.0.
Meaning what, exactly?
It means that every new octave has double the frequency of the previous one. The noise is horizontally squished together more tightly.
It oscillates twice as fast. So if octave 1 creates a sweeping hill that takes a mile to go up and down, octave 2 creates hills that go up and down every half mile.
And octave 3 oscillates every quarter mile. We are introducing finer and finer geometric details.
That is lacunarity. But if we just add those layers together as they are, the world will become an unreadable mess of spikes. Like, if a tiny pebble on the ground has the same vertical height amplitude as Mount Everest, the terrain just looks like static.
Right, we need the smaller details to be physically smaller in height.
Which brings us to persistence.
Represented by the variable p, persistence controls how much the amplitude, the height, decreases between each octave. It is a multiplier, typically a fraction like 0.5.
So octave 1 has a height of 100. Octave 2, because of the 0.5 persistence, only has a maximum height of 50. Octave 3 is 25.
Exactly. The higher frequency details have lower and lower impact on the overall elevation. They just add texture to the larger shapes. And by tweaking the persistence value, a developer can completely alter the geology of the environment.
Give me an example of how changing P changes the world.
Well, if you set a high persistence, say 0.8 stead, the amplitude doesn't decrease very much between layers. The high-frequency octaves retain a lot of strength.
So the small, rapid details are very pronounced, jutting out aggressively.
Yes, this creates turbulent, rough, jagged terrain, like a harsh volcanic landscape or the sharp peaks of the Alps.
And if I turn the persistence down,
If you use a low persistence, say 0.2, the higher frequencies die off incredibly quickly. The small details are practically flattened out, leaving you with smooth, gentle rolling hills like a manicured golf course or the English countryside.
that is brilliant. With just two variables, lambda and p, you can write an algorithm that generates an infinite barren wasteland or an endless Scottish highland.
The math is incredibly flexible.
Now, one of the papers we were reviewing dives into a practical Python implementation of this using libraries like NumPy and Matplotlib, and it highlights a critical mathematical hurdle that happens when you start summing up all these octaves.
Ah, yes. The problem of unbounded values.
Right. If you add up 5 or 6 layers of noise, the final height values at certain coordinates can accidentally stack up and spike way outside your expected bounds. You might want your terrain to exist on a scale of 0 to 1, but suddenly you have a peak that hits 2.5. How do developers handle that?
The paper discusses normalization techniques. You have to take this wild, unpredictable data and scale it back down into a strict, usable range. The most common and simple method is min-max normalization.
How does that work?
The computer finds the absolute highest peak in the entire terrain chunk and the absolute lowest valley. It then linearly scales every single point proportionally between those two extremes, snapping them between 0 and 1.
But the paper argues against relying solely on min-max, suggesting it can actually ruin the terrain. Why?
Because min-max normalization is completely linear and highly vulnerable to outliers.
Outliers.
Imagine your terrain generation creates a mostly flat, interesting landscape, but due to random chance in the noise calculation, a single incredibly tall, needle-like mountain spikes up in the corner.
The outlier.
Right. When min-max tries to normalize that chunk, it has to accommodate that massive spike. So it sets the top of the spike to 1 and the bottom of the map to 0.
Oh, I see. As a result, all of your normal, interesting terrain features the subtle rolling hills, the shallow valleys, get mathematically squished down into a tiny decimal range just to make room for the spike.
Your world will end up looking incredibly flat and boring, punctuated by one bizarre geometric anomaly.
So how do we fix that without flattening the world? The source suggests TON normalization.
TON, which stands for the hyperbolic tangent function. Unlike min-max, TON is a nonlinear curve. It has an S-shape. It maps any input value, no matter how large or small, to a value strictly between -1 and 1.
What makes it better than min-max?
It treats the data differently depending on where it sits. For values near 0, the average, normal terrain, the TON curve is relatively straight. It preserves the subtle details of your hills and valleys without distorting them much.
And for the outliers?
As values get higher and higher, the curve flattens out asymptotically. It compresses the extreme outliers much more aggressively than the intermediate values.
So it gracefully flattens the tops of the most extreme peaks, bringing them back into a normal range while completely preserving the integrity of the mid-level terrain. It manages mathematical outliers smoothly.
It acts exactly like a soft limiter in audio production, preventing clipping without destroying the dynamic range of the rest of the track.
Okay, so through linear algebra, dot products, fade polynomials, and tan normalization, we have a gorgeous, mathematically perfect 3D height map. But it's just raw geometry. The last step of procedural terrain generation is texturing it. We have to paint the dirt.
Right. The Python script in our source material handles this by defining a calculate map with FBM function. Once the height data is generated and normalized, the script assigns terrain biomes, deep ocean, shallow water, beach, sand, grassy plains, snowy mountains.
How does it know where to put the sand versus the snow?
It uses normalized weights based on the height values. A developer defines the desired proportions. For example, you might want 40% of your world to be ocean, 5% to be beach, 40% to be grass, and 15% to be mountains.
Okay.
The script calculates the cumulative sum of these probabilities to create strict elevation thresholds.
And then it iterates over every single point on the map.
Yes. For every point, it looks at the normalized height and uses a binary search algorithm to find which threshold bucket that height falls into. If the height is below threshold A, it assigns a dark blue RGB color. If it is between A and B, it assigns a sandy yellow.
And I want to highlight the use of the binary search there. If you have an array of 1 billion pixels, you can't afford to run a slow, linear search to figure out what color every pixel should be.
It would take forever.
A binary search halves the data set with every step, making the color assignment computationally lightning fast, which is the only reason the game doesn't freeze when you load a new area.
Computational efficiency is the invisible architecture of all virtual worlds.
Which actually brings us to a massive pivot point. We have used math to generate an infinitely expanding, beautifully textured terrain. It has soaring mountains and deep valleys. But if we actually try to render this world right now, we have a catastrophic problem.
We have created too much math, specifically the polygon count.
Exactly. The computer actually tries to draw every single mathematically perfect polygon, every pebble, every fold in the valley, all the way to the horizon, miles away. The GPU will be overwhelmed.
The frame rate will drop to 0, the computer will crash.
This is where we transition from the pure, idealized math of world building to the harsh engineering realities of computer science. We need a way to manage visual complexity.
We have to cut corners without the player noticing.
And that leads us into our next major focus, managing the polygons. For decades, the solution to this problem has been a concept called level of detail, or LOD. Let me give a real-world analogy for the scholars listening.
Please do.
Think about LOD like streaming a video on your phone. When your cellular connection is strong, you stream in crisp 4K resolution. But when you drive into a tunnel and your bandwidth drops, the video player doesn't just stop and crash, it dynamically drops the resolution to 480p. The image gets a bit blurry, but the video keeps playing smoothly without buffering.
LOD applies that exact same philosophy, but to 3D geometry instead of video pixels. It is the art of trading absolute visual fidelity for interactive performance.
It dynamically simplifies a 3D object based on its importance to the viewer. If you have a highly detailed 3D model of a rock made of 10,000 polygons, it looks great up close.
But if that rock is 2 miles away in a game world and it only takes up 3 literal pixels on your screen, drawing 10,000 polygons for 3 pixels is a colossal waste of processing power.
A version of that rock made of 10 polygons will look identical from that distance.
That is the core logic. But while the concept is simple, implementing it in a graphics engine has historically been a nightmare for developers. It required massive, heavy, complex systems.
And one of the primary sources we are examining focuses on a major historical milestone in this field, the GLOD API. Geometric level of detail.
Right.
The paper lays out the landscape before GLOD existed. It says developers essentially had 2 bad options. You either had to write your own custom mesh simplification algorithm from scratch, which is mathematically brutal, or you had to use a massive overarching system called a scene graph, like a program called Performer.
Scene graphs were powerful, but they were incredibly restrictive. They were described in the literature as heavyweight, all-or-nothing solutions.
Why were they all or nothing?
Because a scene graph didn't just manage the polygons. It demanded total control over the software's architecture. If you wanted to use Performer for your LOD management, you couldn't just plug it in. You had to build your entire game engine around it from the ground up.
Wow.
You had to use their memory management systems, their specific data structures, their culling algorithms. For many developers, it was too invasive.
Enter GLOD. The paper details how GLOD took a completely different approach. It was designed as a lightweight OpenGL extension.
Yes. The developers of GLOD were heavily inspired by a system called Chromium. Instead of forcing game developers to rewrite their entire engine to accommodate a scene graph, GLOD operated via interception.
I love this part of the paper. It has essentially acted like a man-in-the-middle attack, but for optimization.
That is a perfect way to describe it. A developer writes their normal OpenGL code, the standard instructions sending polygons to the graphics card. But GLOD secretly intercepts those draw calls before they hit the hardware.
It masquerades as the graphics driver itself.
Exactly. It looks at the geometry, simplifies it on the fly based on the LOD rules, and then passes the lighter, optimized version down to the actual GPU.
It's brilliant. The engine doesn't even know it's being optimized. It provided a simple programming interface without demanding an architectural overhaul.
But to do this efficiently without creating visual glitches, GLOD had to organize the geometry very carefully. The paper outlines a specific data flow model.
Let's get into that hierarchy.
Let's start at the bottom. The fundamental geometric primitive in this system is called the patch.
What defines a patch?
A patch is the smallest atomic drawing unit in GLOD. It is a block of geometry that shares a single rendering state.
Let's translate that. A rendering state means all the polygons in that block use the same texture, the same material properties, the same shaders.
Correct. You cannot break a patch down into smaller pieces without messing up the rendering instructions. If a character model has a leather jacket and blue jeans, the jacket is one patch and the jeans are another because they require different materials to render.
Okay, so the patch is the foundation. What sits above the patch in the hierarchy?
Above the patch is the object. An object is a collection of patches that are combined together during a build process into a single multi-resolution hierarchy.
And why do we need objects?
The primary reason objects exist as a structural concept is vital to visual integrity, preventing cracks.
Cracks in the geometry. I remember playing old PC games where you could sometimes see through the seams of a character's shoulder.
Exactly. That happens when different parts of a model are simplified at different rates without communicating. Let's use a car model as an example.
Okay.
The car door is made of a red metal patch. The window is made of a transparent glass patch. If the LOD system decides to simplify the red metal door to save polygons, it might move or delete the vertices along the top edge.
But if it doesn't simplify the glass window at the exact same time, in the exact same way, the vertices where the metal meets the glass will drift apart.
A gap will open up. You'll see right through the car.
So by grouping those dependent patches into a single object, the GLOD system understands their relationship.
It maintains the connectivity and shared boundaries between adjacent patches as it mathematically simplifies them, ensuring that no topological gaps or cracks appear.
That solves the integrity problem. And then at the very top of the hierarchy, above objects, we have groups.
A group is a collection of object instances. And in the GLOD architecture, the group is the fundamental unit for adaptation. It is the container where you define your adaptation criteria, the strict rules for when and how much the geometry should be simplified.
The budget.
Yes. The paper mentions two main ways to establish this budget. The first is based on screen space error thresholds.
How does that work?
You can tell the system, simplify these objects as much as you want, but the simplified silhouette cannot deviate by more than 3 pixels from the original high-poly model on the user's screen.
So it guarantees a specific level of visual quality regardless of performance.
Right. The alternative is a strict triangle budget. You tell GLOD, I don't care how it looks, you have a maximum of 50,000 triangles for this entire group of trees. Figure it out.
And it does.
GLOD will intelligently distribute that budget. If you have 10 identical tree models in the group, it will heavily simplify the ones furthest away from the camera while keeping the close ones detailed, dynamically balancing the math to stay strictly under the 50,000 limit.
The engineering behind GLOD is really impressive. The ATI mechanics were relatively straightforward too. Developers used functions like glod_new_group to create the container, glod_insert_object to add the geometry, and utilized vertex arrays to cleanly capture the input data.
It was a massive leap forward for its era.
But let me push back a bit. I'm thinking about modern open-world games. Environments with dense cities, sprawling forests, literally billions of polygons. Having a team of artists and programmers manually group objects, carefully assign triangle budgets to different parts of the scene, meticulously manage patches to avoid cracks. That sounds like an agonizing amount of manual labor.
It was agonizing. Traditional LED management became one of the biggest production bottlenecks in modern development. Artists had to manually sculpt 3 or 4 different versions of every single rock, chair, and tree, a high poly version, a medium poly version, a low poly version, just so the engine could swap between them.
Which inflates file sizes massively and takes months of work.
You are identifying the exact breaking point of traditional LED. The GLOD paradigm, while foundational, simply does not scale to the level of cinematic detail demanded today. And that is why the industry is currently undergoing a massive paradigm shift.
Which brings us to the modern solution highlighted in our sources. Unreal Engine 5 and Nanite.
Nanite.
This is the technology that has fundamentally broken the old rules.
Huh.
How does Nanite evolve past the GLOD concept?
By abandoning the idea of manual LODs entirely, Nanite fundamentally shifts the paradigm by virtualizing the geometry.
What does virtualization actually mean in this context?
It means the engine abstracts the geometry away from traditional polygon rendering. With Nanite, an artist no longer makes low-poly versions of their assets. They can take a source file used for a Hollywood film, a photogrammetry scan of a cliff face comprising 20 million polygons, and drop it directly into the game engine as is.
And the GPU doesn't instantly catch fire.
Because Nanite automatically processes that high-density mesh during the import phase. Under the hood, it algorithmically breaks those 20 million polygons down into hierarchical clusters of microtriangles.
So it's doing the grouping and patching the GLOD did, but automatically on a microscopic scale.
Yes. And at runtime, as you move the camera through the world, Nanite dynamically and continuously streams in only the exact clusters of detail that are visible and relevant to the pixels on your screen. It culls everything else.
Wow.
If a million polygon rock is far away and only takes up 10 pixels, Nanite only streams in 10 polygons worth of clusters.
It evaluates the geometry on a pixel-by-pixel basis in real time. It completely removes the manual effort of LOD management, allowing artists to focus purely on the visual design without worrying about triangle budgets.
It is the culmination of decades of rendering math.
Okay, let's take a breath and survey where we are. We have an infinite terrain built with the linear algebra of Perlin noise and fractal Brownian motion. And our engine can now render billions of polygons smoothly using the virtualized geometric clusters of Nanite. The world is structurally sound.
But right now, it is a dead world.
Yeah, it's just bare rock and dirt. Let's populate it. Let's breathe some life into it. This brings us to the next phase of our synthesis: flora, fluids, and AI.
A convincing natural environment requires vegetation and water, and generating these procedurally introduces entirely new, complex mathematical challenges. Let's start with vegetation, specifically trees and forests.
How do you mathematically describe a tree? If I look at an oak tree, it just looks like a chaotic explosion of branches.
It appears chaotic, but botany follows very strict developmental patterns. To model this mathematically, computer scientists rely on a framework called L-systems, or Lindenmayer systems.
Named after Aristide Lindenmayer.
Yes, a Hungarian theoretical biologist who introduced the concept in 1968. Fascinatingly, he didn't invent them for computer graphics. He invented them to model the biological cellular development of simple weeds and algae.
From modeling algae cells in the 60s to rendering giant virtual forests today. How exactly does an L system work?
At its core, an L system is a parallel string rewriting system.
Let's break that terminology down. A string rewriting system, like a search and replace function in a Word document.
Similar, but with a crucial distinction. In a word processor, if you tell it to replace every A with AB, it searches sequentially from the start of the document to the end. An L system is parallel. It applies the rules to every single letter in the string simultaneously in a single generation step.
Why is parallel replacement important?
Because it models biological growth. When a plant grows, all of its cells are dividing at the same time. The bottom leaves don't wait for the top leaves to finish growing before they start. Parallel rewriting mathematically simulates time.
Okay, that tracks. The paper defines the math of an L system as a tuple. L equals m omega r. Let's decode that tuple for our scholars.
M represents the alphabet. This is the set of symbols or letters we are allowed to use. Omega is the axiom. This is the starting string, the initial seed of the plant. And R is the set of production rules.
So if my axiom omega is the letter B, and my rule R is that every B turns into FB, in generation 1, I have B. In generation 2, I apply the rule, and it becomes FB. In generation 3, I apply the rule again to the new string. The F stays an F, the hyphen stays a hyphen, but the B at the end turns into FB. So the string is now FFB.
It grows exponentially longer with every step.
Exactly.
And modern L systems are parameterized, meaning the letters can carry mathematical values. A rule might look like A of P becomes A of P divided by 2, meaning if you find a module A with a length parameter P, replace it in the next generation with an A where the length is cut in half, simulating branches getting thinner as they grow outwards.
But this is where I get tripped up. We are generating massive strings of letters, F's, B's, plus signs. How does a string of text on a screen become a 3D tree?
It requires an interpreter, and in graphics, that interpreter is often a concept called turtle graphics.
Oh, like the old logo programming language from the 1980s.
Precisely. Imagine a tiny virtual turtle sitting in your 3D space holding a pen. The turtle reads the L string sequentially from left to right and interprets the letters as geometric commands.
For example, the letter F tells the turtle to draw a branch and move forward.
Yes. And the symbols control the orientation. A plus or minus might tell the turtle to yaw left or right. A backslash or forward slash tells it to roll. The ampersand and caret symbols command it to pitch up or down. By reading the string, the turtle physically draws the geometry in three-dimensional space.
But there is a glaring mechanical flaw here. A turtle drawing a single continuous line can draw a squiggly snake, but it cannot draw a branching tree. Once the turtle goes down a branch to draw a leaf at the very tip, how does it get back to the trunk to draw the next branch? It can't just draw a line backward over its own path.
This was the genius of Lindenmeyer's expansion, bracketed L systems. He introduced the left bracket and the right bracket into the alphabet.
What do the brackets do to the turtle?
They interact with the computer's memory stack. When the turtle reads a left bracket, it immediately pushes its current state onto the stack. It saves its exact XYZ position and its exact pitch, yaw, and roll orientation.
I have an analogy for this. For the scholars out there who play RPGs, reading a left bracket is exactly like hitting quick save right before you walk into a terrifying boss room. You push that save file into memory. If you walk in, explore a branching path, and hit a dead end, you hit load. You pop the save file. That is the right bracket. When the turtle reads the right bracket, it pops the state off the stack, instantly teleporting back to the exact position and orientation of the quick save, ready to try a different path.
That is a flawless analogy. In the context of a tree, the turtle draws the trunk upwards. It encounters a left bracket, saving its spot on the trunk. It then reads commands that send it shooting off to the right, drawing a complex branch with leaves. When it hits the closing right bracket, it instantly teleports back to the trunk, reorients itself, and reads the next command to draw the left branch.
This recursive pushing and popping of the memory stack is what allows for incredibly complex, nested, overlapping branching structures. It is mathematically elegant.
It is elegant in theory. But in practice, as highlighted by a fascinating research paper from Purdue University in our stack, it is a nightmare for artists.
Why?
Because L systems are essentially a complex, low-level, non-intuitive programming language. If an artist has a specific vision, say they want a tree that looks specifically like a weeping willow, with drooping branches trying to figure out the exact magical sequence of math rules, angles, and bracket combinations by blind trial and error is excruciating.
You change one number in the axiom, and suddenly your willow tree turns into a spiky cactus.
Exactly. The forward process, turning rules into a tree, is easy. The inverse process, looking at a tree and guessing the rules, is incredibly difficult. And this is where the AI intervention we are studying comes into play. The Purdue paper introduces something revolutionary: latent L systems powered by transformers.
Transformers. When people hear that today, they immediately think of large language models.
Yep.
ChatGPT, Claude.
It is the exact same underlying architecture. But think about what a transformer actually does. It excels at understanding, translating, and predicting sequences of tokens. Usually those tokens are words in an English sentence. But an L string is just a sequence of tokens, too. It has a grammar, it has a syntax, with brackets acting like punctuation.
Oh, wow. I see where you're going with this. They trained a language model not on human languages, but on the language of trees.
Precisely. The researchers trained the transformer on vast datasets of 3D tree models and their corresponding L strings. Using self-attention mechanisms, the AI learned the hidden, latent rules of tree topology. It learned that a left bracket opened 40 tokens ago needs a right bracket to maintain structural integrity.
It learned generative botany. So now, instead of a human programmer spending a week manually tweaking angle parameters to build a pine tree, the AI can generate the perfect L string instantly.
And it works astonishingly well. The paper reports that the AI generates new trees with 97.2% accuracy in branch lengths compared to the input data, and over 92% accuracy in other complex geometric features. It successfully captures the intricate branching topologies that previously required painstaking manual coding.
The AI learned the grammar of nature. So we've got our infinite procedural terrain, and now it is covered in AI-generated, perfectly branched forests. Let's add some water to this ecosystem. Let's talk about real-time fluid dynamics.
Simulating water is notoriously complex because fluids, unlike rocks or trees, do not have a static shape. They constantly deform, collide, and react to their container. To solve this, physics engines rely on the Navier-Stokes equations, which are complex nonlinear partial differential equations describing the motion of viscous fluid substances.
Our sources break down two distinct approaches used in modern engines to approximate Navier-Stokes, Eulerian and Lagrangian. Let's define those.
The Eulerian approach is grid-based. Imagine setting up a stationary invisible grid over a river. You don't track the water itself. Instead, you look at each stationary cell in the grid and calculate how fluid properties like pressure, density, and velocity move through that specific cell over time.
It's like standing on a bridge with an anemometer, measuring the wind as it blows past your specific location.
Exactly. The Eulerian method is fantastic for calculating complex pressure dynamics, making it great for large bodies of water or smoke. But it can struggle to maintain fine details. The fluid can look a bit blurred.
And the Lagrangian approach.
The Lagrangian approach is particle-based. Instead of a fixed grid, you track thousands of individual independent fluid particles as they move through space. Each particle carries its own mass, position, and velocity.
It's like tossing 1,000 rubber ducks into the river and tracking exactly where each duck goes.
A perfect analogy. This particle method is excellent for preserving mass and simulating highly dynamic, chaotic movements, splashes, sprays, foam. But calculating how thousands of particles collide and push against each other without a grid to organize the pressure is computationally devastating.
So which one do modern games use?
The source mentions Unreal Engine's Niagara Fluid plugin, specifically using something called a Grid 2D FLIP pool. FLIP stands for Fluid Implicit Particle. It is a hybrid approach.
It combines both the ducks and the bridge.
Exactly. It uses Lagrangian particles to track exactly where the water is and capture the chaotic splashing details. But to calculate the complex pressure equations, how the water pushes against itself, it temporarily maps those particles onto an Eulerian grid, solves the math efficiently, and transfers the velocities back to the particles. It leverages the strengths of both to achieve real-time performance.
But here's where it ties beautifully back to the beginning of our deep dive. The water isn't just a visual effect sitting on top of the terrain. The physics interact with the math.
Hydraulic erosion.
Yes. The sources detail how simulating shallow water flowing over the Perlin noise terrain actually changes the geometry. As the simulated water flows downhill, guided by those gradient vectors we calculated earlier, it exerts physical force.
It picks up mathematical sediment from the peaks, carries it down the slopes, and deposits it in the valleys.
Over time, this physically based simulation permanently scars and shapes the algorithmic terrain. It carves realistic riverbeds, creates alluvial fans, and softens the sharp ridges of the fractal Brownian motion. It adds an immense layer of natural geological realism that pure noise math alone cannot achieve.
It is the synthesis of procedural generation and physics simulation. You use math to build the rock, and then you use physics to break the rock.
Okay. We have reached the final stage of world building. We have a deeply complex, mathematically robust world. Mountains eroded by rivers filled with AI-generated forests. But if we render this scene right now, without any atmospheric math, it is going to look completely flat. It will look like a brightly colored plastic toy.
Because we haven't simulated optics, we haven't introduced light.
Exactly. To make it photorealistic, we have to simulate exactly how real light hits these mathematical objects. We need to polish it by simulating light with PBR and Lumen.
This represents the holy grail of modern computer graphics. Up until relatively recently, rendering engines used very hacky artistic approximations to make things like shiny or dull. An artist would manually paint a white spot on a texture to fake a reflection. But PBR, which stands for physically based rendering, changed the entire industry by enforcing actual mathematical optics.
What is the core physics principle behind PBR?
It centers around microfacet theory and the BRDF, the bidirectional reflectance distribution function. But at a high level, it is governed by one unbreakable rule: the conservation of energy.
Conservation of energy, meaning an object cannot reflect more light than it receives from a source.
Exactly. In older games, because the math was arbitrary, you could have a glowing plastic box that somehow looked brighter than the sun hitting it. PBR enforces physical reality. When a beam of light hits a surface, the energy is split. Some of that light is absorbed into the material and scattered internally, that is diffusion, which gives an object its base color. The rest of the light bounces off the surface, that is reflection.
And the math guarantees that the diffused light plus the reflected light never ever exceeds 100% of the incoming light.
Correct. And PBR defines materials using specific real-world optical properties. One of the most important is metallicity. The math treats metals and dielectrics, nonmetals like wood or plastic, entirely differently.
How so?
Nonmetals absorb light and scatter it, so they have a diffuse base color, and their reflections are generally white, picking up the color of the light source. Metals, however, do not have diffuse color. They absorb all internal light instantly. They only have reflections, and the reflections are tinted by the color of the metal itself, like gold or copper.
The sources also highlight Fresnel reflection. I love this one because it's a phenomenon you see every day but rarely think about. For the scholars listening, Fresnel is the reason why a lake looks completely transparent when you stand on a dock and look straight down into it, but looks like a perfect opaque mirror reflecting the sky when you look at it from a shallow angle across the horizon.
It describes how the reflectivity of a surface increases as the viewing angle becomes shallower. PBR calculates that angle of incidence perfectly for every pixel.
And it goes even deeper. Subsurface scattering mathematically models how light penetrates a translucent surface like human skin, leaves, or wax, bounces around inside the cellular structure, and exits at a different point, giving it that soft, fleshy glow.
And the sources note that this physical modeling is extended to volumes as well. Atmospheric effects, light scattering through participating media, calculating how photons bounce off water molecules in fog or dust in the air, creating physically accurate day-night cycles and God rays.
And to get these material properties right, developers don't just guess the math anymore. They use photogrammetry. They literally go out into the real world with specialized cameras, scan real bark and real rocks, and encode their exact optical properties, how rough they are, how metallic they are, into the digital textures.
The materials are objectively true to reality.
Okay, I have to jump in and challenge this.
Yeah.
Because everything you just described, the BRDF, calculating Fresnel angles, tracking subsurface scattering, simulating photons bouncing off dust in the air, that sounds incredibly, impossibly computationally expensive.
It is.
If PBR requires us to calculate the angle, bounce, and absorption of billions of photons hitting surfaces from a light source, how on earth are real-time engines doing this at 60 frames per second? Simulating full light bounces path tracing is what movie studios like Pixar do, and it famously takes a server farm hours to render a single frame of animation.
You are absolutely right. Fully calculating the rendering equation with millions of light rays is far too slow for real-time interactive media. And that is exactly why Epic Games introduced Lumen in Unreal Engine 5. Lumen is, for lack of a better term, the ultimate cheat code for real-time global illumination.
Global illumination meaning light that bounces. Light hits a red wall, bounces off, and subtly dyes the adjacent white floor red. How does Lumen cheat that math without looking like a cheat?
By relying on a series of ingenious approximations and heavily optimizing where the engine spends its calculation time. In the past, to get global illumination in a game, developers had to bake the lighting. They would use server farms to calculate the light bounces overnight and then permanently paint those shadows and red glows directly onto the floor textures.
But baked lighting is static. If you blow up the red wall in the game, the red glow on the floor would still be there, painted on. It breaks the illusion.
Lumen achieves fully dynamic global illumination without pre-baking. If the wall falls, the light updates instantly. To do this, the architecture synthesizes several techniques. First, it uses surface caches. It captures and stores highly simplified lighting information for objects, calculating the complex math at a much lower resolution internally.
It also uses distance fields, right?
Yes. Mesh distance fields calculate how close objects are to each other mathematically without doing full polygon intersection tests. This allows Lumen to rapidly estimate shadows and ambient occlusion. It knows a corner is dark because the walls are close together without tracing 1,000 rays to prove it.
The documentation also emphasizes screen space data, meaning the engine heavily reuses the lighting information already calculated for the pixels currently visible on your monitor to estimate the lighting for things just off screen.
And it does all this while seamlessly blending with hardware ray tracing. If your GPU has dedicated ray tracing cores, Lumen uses them for precision. If it doesn't, Lumen smoothly falls back to software tracing. It fakes the bounce by being incredibly smart about what it chooses not to calculate.
It prioritizes the visual result over the brute force physics. And it synthesizes all these approximations so fast that the human visual cortex cannot tell the difference between Lumen and a Hollywood render that took 12 hours.
The illusion is complete.
So bringing it all together for the scholars of Edward Little High. Think about the journey we just took. We started with an empty void. We used the linear algebra of gradient vectors, dot products, and fading polynomials to build an infinite procedural terrain. We utilized the interception of GLOD and the virtualized microclusters of nanite to render billions of polygons without melting our hardware. We used transformer AI language models to write L-system code, growing mathematically perfect forests. We used Eulerian and Lagrangian fluid dynamics to simulate rivers eroding that terrain. And finally, we illuminated the entire scene with real-world PBR physics and the ingenious light-bouncing approximations of Lumen.
It is a breathtaking synthesis of mathematics, physics, and computer science. The tools we have discussed are not just for games. They are used in architectural rendering to see how sunlight hits a building before it is constructed. They are used in film production for virtual sets. They are used to create digital twins of cities for urban planning.
The applications are limitless, but it does leave us with a final mind-bending thought to consider.
Right now, these systems we've discussed, the algorithms generating terrain, the transformers writing pre-strings, nanite virtualizing geometry, lumen faking light bounces, they're discrete, separate tools. They're instruments played by human developers, artists, and programmers to carefully craft a digital world over years of production.
But we already see AI understanding 3D topologies.
Exactly. How long until an overarching AI architecture can synthesize all of these discrete steps natively? How long until an AI can dynamically generate a fully textured, physically accurate, and infinitely detailed universe in real time based on nothing but a single text prompt from a user?
Just typing a prompt. Generate a dark fantasy forest with a raging river set at dusk. And the math just manifests it instantly. Will manual world design become completely obsolete?
It is the next logical horizon for everything we've analyzed today.
That is wild. Well, scholars, the next time you boot up a simulation, watch a CGI film or look out a virtual window at a digital mountain. Remember the millions of dot products, the L strings, and the virtualized clusters tricking your visual cortex right in that exact moment. Don't just accept the illusion. Understand the math that built it. Thank you for joining us on this deep dive and keep questioning the digital spaces you explore. Catch you next time.